Today, we're taking an exclusive first look at a tool that could seriously change the game for drug discovery. It's called PyDescriptorC, and it's all about cracking the secret 3D language of molecules.
But before we dive in, let me just ask you something. What if the very molecule that's supposed to be a cure could also be a poison? I know, it sounds like something out of a movie, but this is a real high-stakes problem that chemists face every single day.
And the most tragic, infamous example of this is the drug thalidomide. See, back in the 50s, one version of it was a fantastic treatment for morning sickness. But its perfect mirror image, chemically identical, just flipped like your left and right hand, that version caused absolutely devastating birth defects. This wild phenomenon actually has a name. It's called Chirality Cliffs. It's where that tiny tweak in a molecule's 3D shape, its handedness, causes this massive, cliff-like drop in how well it works, or even worse, makes it dangerously toxic. So you can see why understanding this is absolutely crucial.
And here's the kicker. For decades, a lot of our most common computational tools have been, well, effectively blind to these subtle but life-or-death differences. They can read the chemical formula, sure, but they can't always tell the left hand from the right. And that gap has been a huge roadblock for medicine.
So it's time to introduce the hero of our story, PyDescriptorC. This is a breakthrough tool developed by Mawson and his team, and it's designed to do one thing: solve the problem of chirality cliffs by finally letting us see these 3D differences.
So what is it really? At its heart, PyDescriptorC is a powerful Python script that plugs right into the popular 3D viewing software PyMOL. And its main job is to analyze a molecule's shape and translate all that complex 3D info into cold, hard numbers, data that a computer can actually understand and learn from.
All right, let's get into the deep dive, because the sheer scale of what this thing can do is what makes it so revolutionary. We're going to pop the hood and look at the raw power here. Okay, get ready for this. For every single molecule you give it, PyDescriptorC calculates over 112,000 molecular descriptors. Now, think of descriptors as a molecule's digital fingerprint. They describe everything about it: its size, its shape, its charge, all of it. This is how a machine can finally see the molecule. But here's the magic number. Out of that huge amount of data, more than 15,000 of those descriptors are what we call chirality aware. These are brand new calculations specifically designed to describe the unique 3D space around that handed center, the exact thing that other tools just miss.
And this, right here, is why it's a total game changer. Most of the free tools out there, they either ignore this information or they just kind of lump it all together. PyDescriptorC is the first tool of its kind that gives us this incredibly rich, specific vocabulary to describe a molecule's handedness. It lets our AI models finally tell the difference between the cure and the poison.
Okay, so you're probably thinking a tool this powerful has got to be a total nightmare to use, right? Well, you'd be wrong. The team designed the workflow to be incredibly simple, fast, and of course, powerful.
It's really just a straightforward three-step process. First, you get your 3D molecules ready in a standard file format. Step 2, you run the script inside PyMOL. And finally, Step 3, it spits out this beautiful, clean CSV file with all 112,000 plus descriptors perfectly ready for machine learning.
And this is basically what it looks like. You can see how streamlined it is. It takes what used to be a really complex, messy process and just simplifies it, turning one little file into this incredibly rich data set. That's a huge time saver.
Oh, and did I mention it's fast? Like, ridiculously fast. It uses multiprocessing, so it can chew through a complex molecule and generate that entire digital fingerprint in about 1.6 seconds. That means you can screen huge libraries of potential drugs in days instead of months.
Of course, big numbers and speed are great. But the real question is, does it actually work? Well, seeing is believing. Let's look at the proof, because the case studies from the paper show exactly how this tool succeeded where others have failed.
So, the first test was on a set of molecules called HDAC4 inhibitors. These are being looked at for cancer treatments, and it's a class of drugs where we know chirality is super important for them to work properly. Just look at this pair. They are perfect mirror images of each other, but the one on the left is almost 4 times more powerful than the one on the right, a classic chirality cliff. The model built with PyDescriptorC totally nailed it. It found one specific descriptor that perfectly explained the difference in activity.
That's how you find a better cancer drug.
Now, to prove this wasn't just a lucky guess, the team threw a totally different problem at it. A set of ADAM17 inhibitors, which are being studied for things like inflammatory diseases.
And what do you know? It happened again. The molecule on the left is over 4 times more potent. This time, a different chirality-aware descriptor was the key. And again, the model correctly figured out why, linking a specific 3D feature to the drop in activity. It decoded the reason behind the cliff.
You know, the authors themselves really summed it up perfectly. The models they built didn't just have great stats. They actually explained the molecular basis, the why, behind these activity cliffs. That is the holy grail for this kind of work.
So, if you're in any way involved with drug design, this is a tool you need to have on your radar. Let's wrap up with why PyDescriptorC really needs to be in your computer-aided drug design toolkit.
First off, it's platform independent. It'll run on anything. It's open source for academic use, so it's accessible. The workflow, as we saw, is super user-friendly. And most important, it's powerful. It unlocks those crucial insights that can be the difference between a dead end and a breakthrough discovery that could lead to safer, better drugs for all of us.
By finally giving us a language to properly describe and understand chirality at a massive scale, PyDescriptorC has really opened up a whole new door in drug discovery. Which leaves us with one final, very exciting question. What hidden molecular patterns will you unlock?